Hello all, welcome to this tutorials in which we will be running through the recurrent neural networks, RNNs, LSTMs and GRUs. The aim of this tutorial is to understand these different cells, RNN cell, LSTM cells and GRU cells, and then put them together, come up with the deep networks that are for using RNNs, LSTMs, and GRUs. So most of our discussion here will be for a classification task, but the same thing can be extended for a sequence to sequence mapping as well. So without any further delay, let's jump into understanding RNNs from the lens of implementations. So by now, all of you are comfortable that I have an input X, which has sequences with timestamps x1, x2, so on till xt. And please remember, this is one given example. Okay, so we're not putting I and making more clutter into the notations. Okay, now here at any time step t, now this belongs to rd. Okay, so and then so always we'll be putting in batches. So the batch size. So let's consider B as the batch size, and then the total sequence length of this example, the sequence length, let's consider the sequence length as T, and then input feature dimension is D. See, whenever we are saying the input feature dimension is D, what do we mean by that is that we are considering an embedding of this first word. So since we are dealing with RNNs, deals with sequences, assuming that we are dealing with words. Now, first word, it can be either represented as one hot encoding, or this can be represented as an learnt embedding. Okay, now, both are perfectly fine. So to understand the overall idea, now whether it is being a one hot encoding or being a embedding doesn't stop us from understanding. Now, in terms of implementation, whenever you are having embeddings, that is always considered to be giving good results. Okay, fine. So now, all of these models now will have this hidden state. Okay, h t minus 1. This belongs to the hidden state sizes rh. And this is the hidden dimension. Okay, and then y for that given example, it belongs to rk. This is the output dimension. Okay, for the given example x. Okay, so now we know that now if you put all these x together, now x, the whole x, now will be a matrix which is t cross d. You have t length sequence, and each is of dimension t. So it's a, and if you consider the batch, okay, once the batch is considered, once the batch is considered, I represent it as x, that belongs to R B cross T cross D. And whenever we have this batch as the first dimension, okay, now this is what is known as a batch first. Okay, now here the batch size is the first dimension. So now let's recall the overall RNN equations. The reason why I'm doing is, we have to know what is the size of each of those weights that we are having. Okay, so now let's look at the RNNs. RNNs, we compute HT equals some activation. Okay, now irrespective of that, W1 XT plus W2 ht minus 1 plus b1. See, and then please remember that this ht which is there is the hidden dimension. This has to be of size rh. So this is for one uh, instance, one timestamp. Okay. So now at the timestamp t, what is the hidden dimension? So please remember that this should belongs to RH. Okay. Now finally, whatever we get should belongs to RH. So now what do you mean by that? Now finally, it should belongs to RH. Now these are additions. Then what do you mean by that? This should belong. All of them individually should belongs to RH. Correct. So now that is what we have to define now. Now this W1 which is there will be a matrix that is H cross D. Okay. So and then W2 belongs to R H cross H and B1 belongs to RH. Okay. Now this is in RD. Okay. You consider D cross 1. So this will be belongs to RH. This will also belongs to RH. This is already in RH. You add them, okay, and then pass it through a sigmoid, and sigmoid is applied individually for each of them. So therefore, your or any activation, not only sigmoid. So that means that this will be in RH. Okay. So now this is the hidden state. Now how do you compute the output? See the output y at that given timestamp t is W3 HT plus some B2. And please remember this YT should belong to RK. Correct? Now therefore, this W3 should belongs to R, K cross H, and then this B2 should belongs to RK. Okay. Therefore, this will belongs to RK. This also belongs to RK. Now you add them. So finally, this will belong to RK. Okay. This is how we obtain the RNN. So from this, what we know, no, these are the learnable weights. Okay. Now we have these many learnable weights. You can put some numbers and then think of how many learnable weights are there in this given case. Okay. So now let's go into the GRU. Okay. Uh, so what happens in GRU? Let's look at gated recurrent unit. See, as per the timeline, LSTM came first. Since LSTM has too many weights, now they actually went from reducing it and obtained GRU. But pedagogically, we always look at GRUs first, which is just a straightforward extension of RNNs, and then we look at the LSTMs. Okay. Now let's look at gated recurrent units and understand their implementation. Gated recurrent units. GRUs. Okay. Now here, as we already know from a generalized expression, now in this case, now HT is some alpha T taking a Hadamard product with HT minus 1 plus some beta T, which is taking the Hadamard product with HT tilde. See, now you're taking Hadamard product. Okay, that is element-wise multiplication when you have vectors. So this and this, all of them should be of same shape. Okay. So now that means that from this we can easily say this alpha t, comma, this beta t, comma, ht minus 1, comma, ht tilde, all of them belongs to RH, correct? Which matches the shape that is needed. Now, once you have this HT, now in a similar way like we did in our earlier RNN case, we obtain the Y. Okay. Now, obtaining Y is exactly similar, but obtaining the hidden state is where things matter. So now in GRU, normally what they do is, now this beta t which is there is considered to be 1 minus alpha t. Okay, that is how this beta t comes into picture. So now ht minus 1 is from the previous state, the hidden state input from the t minus 1 step. Now that is there. Now the only question that arises is how do you get this alpha t and how do you get this ht tilde? Okay. Now the way in which we obtain this alpha t is some activation function of some weights w alpha for the concatenated input of xt and ht minus 1 plus b alpha. Now this is a bit weird. Now what do you mean by this? So now this actually means xt concatenated with xt minus 1. This belongs to some r d plus h. Okay. Now this belongs to r d plus h. Now sum of two things. Now alpha t should belongs to rh. Now therefore this has to give me an output of belongs to rh. This also should be in rh. Okay. So now therefore the w alpha which is there now belongs to r h cross d plus h, and this b alpha which is there belongs to rh. Now when you apply this, your alpha t which is there will be in rh. Okay. So now see, just try to understand whenever you have, now these are the weights that are learnable. Okay. Now how many weights will come into picture? As of now we have these many weights for alpha t. Now we have to come up with this ht tilde. Okay. Now to come up with this, they have what do you call? Now rather than directly going ahead and using the previous state, so what they do is they will have some learnable parameters. So and put it as what is known as some residual connection. Okay, the words doesn't matter. So rather than working with directly with the previous hidden state and the input, okay, now what they do is now they will have a learnable things, and that they take the Hadamard product with the ht minus 1. Okay, so now that's what they will do. They call it as the residual thing. Okay, but that's fine. So I don't prefer to call it as R, so I use this symbol. Some activation, the weights pertaining to the residual state. So now xt ht minus 1 plus b of that. Now again, exactly. Now this has to match. Now because you have to take the Hadamard product with the state. So now therefore, now this and this, okay, now they will be of the same dimension, that is there. Okay, so now comes ht tilde to some activation wh. This is xt concatenated with this whatever residual that you have and t minus 1. See, what is that they're doing here is quite simple. As I told you, rather than just going ahead with the hidden state, they're having some more learnable parameters here. Okay, now you have some more learnable parameters which you can actually have control with. Okay, plus this pH. So now again, now because of the size matching, this and this should be similar to the given size. Okay, now then finally what do you do? Now then you have ht is alpha t. Now taking the Hadamard product with the ht minus 1 plus this is 1 minus alpha t. This taking the Hadamard product with ht tilde. This belongs to RH, and then you have yt, which is w3ht plus b3, that we have obtained from our previous discussion from RNNs. Okay, and this is how the transformation actually happens. Now you can see here how many controls you have. Controls here, 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 here. These are the controls that you have to control your outcome. Okay, this is gated recurrent unit, and I'm comfort and I am sure that all of you are able to understand. Now, this is learnable. This is learnable. Okay, now these two are learnable. Okay, that is the overall idea. Okay, see, the point is now here, rather than just learning the hidden state from the input and then the previous hidden state, now what do I do is, now I come up with, I don't work with directly in the input space. What do? I project it onto some other space and then learn things. Now that is what is happening in the gated recurrent unit. Okay, that is the idea. Okay, you have these many weights here. Now let's look at LSTMs, which is even more uh, weight heavy. Okay, in terms of weights. Okay, now we have this LSTMs, that is long short term memory unit. Okay, or memory cell. Normally these individual units are called as cells. See, the same weight sharing will be there across the time. Okay, now if you use it for whatever you use it for the first input uh, sequence, the same thing used for the second one, the same thing, you unroll it. The idea of unroll is clear. Okay, now this is parameter sharing across the time. In CNNs, what we have is parameter sharing across the space. Okay, so now let's look at these LSTMs. Now I'll leave the generic formulation derivation. So in the sense, how do you represent your LSTMs using this generic formulation? I will leave it to you as a nice exercise. So I'll just write the way in which it is implemented in most of our textbooks or in the blogs that you might read. Okay, so normally you have three controls in LSTMs. Now they name it as forget cell, input cell, and output cell. That's what they name it as. But you have 3 points of control. Okay, and you remember that we came up with LSTMs for a specific reason, that there is a vanishing gradient. Now that means that you need a path in which we actually have no weight interaction. Okay, let me show you. There is a very this STM image that we have. So now this is the standard LSTM image. I just got it from the internet. Okay. So now this is what is known as the candidate state, and this is the hidden state. Hidden state is what something we have been using. See, hidden states are actually having a lot of interaction with the weights. Okay, I'll tell you the weights interaction here. But in the candidate state, that is what they call it, cell state or the candidate state. Now here you see that there is just some multiplication with some number here, and then there is some addition. Okay, you actually have no interaction with the weights. Now this is where the untransformed input actually comes to the next unrolling. Okay, now here is where all your what do you call operations actually happens, where a lot of weights are there. Now no, normally they give a explanation something like, now here you are obtaining, this is what is known as a long term, and this is what they call it as a short term. So just telling those words so that whenever you read other blogs, you are comfortable with that. See, this what they're saying is whatever is coming now, how much I have to remember. Okay, now that is coming from that percentage is coming from the forget gate, and how much new information is added. Now that is coming from this input gate. Now depending on that, how much should be the modification in the hidden state. Now that is given by the output gate. That is what these three gates actually specify. But we have a lot of control. That's what we have a lot of parameters using which we can control the forget gate, the input gate, and then the output gate, in which you have a lot of control. Okay, so now the overall idea is rather than handling in the original data space, now I'll have learnable parameters so that I can project it onto some higher dimension space in which I have the control in the learned space. Okay, fine. So now at any given step, so this is the forget cell. Okay, I just represent them. So and one more thing is I should remember this at any given time, the CT, which is the candidate cell, and then the HT, which is the hidden state. Now all of them will be in RH. Okay, both of them will be in RH. Now we have this FT, which is some activation function. Preferably we use a sigmoid function as it is given here. So weights to control it. XT concatenation of -1 plus I'll not be rewriting the dimension of all these things. Now, since so all of them now will be all the weights that here, all the W's will be in R H cross D plus H. All the biases that are there will be in RH. Okay, now it is constant for all these operations. Okay, while computing the HT. This is what is the forget gate. Now this is what is happening here. This is the interaction. Now that is there. And then we have the input gate. Input gate is again WI XT HT -1. Okay, this will give you some kind. This is again a sigmoid activation, some kind of a percentage. Now it will give you. Now how much percentage should be added? Now this is your input gate. Now how much percentage should be added is obtained here, and the information is obtained here. This is the common terminologies that they use. Okay, but for none of these, we repeat it again and again. We don't have any evidence that these are all in some projected space working. That's all. Now, C tilde. This is what they call it as a candidate input. For this, they use tan H activation. WC XT HT -1 plus WC. Okay, this is the candidate. So now what will be your final CT? CT is now whatever is FT, that you take the Hadamard product with CT -1 plus whatever is your input, that you take the Hadamard product with. So now what does this mean? Now this is from the previous cell state. Whatever you are getting, now this is some kind of a percentage. You make an interaction. Okay, Hadamard product. This is some kind of a percentage. Now you have your data and the hidden state projected onto some higher dimension. You take the interaction. This is what this will be. Okay, this is what will be the CT. This is your long term. This is also known as the long term. Now you have to get your HT. Now to get the HT, now you need this output gate OT some alpha times WO into the concatenated HT -1 plus BO. So and then HT equals OT concatenated with tan h of CT. Now again, since you have a sigmoid, now you can think of it as some kind of a percentage vector for each of the value which is there, and then you are taking a transformation CT here. Now this will give you HT. Now once you have HT, now we have YT, which is W3 times HT plus B3. Now just for the sake of completeness, I just write WF, WI, WC, WO. All of them belongs to R H cross B plus H, BF, BI, BC, BO. All of them belongs to RH. And then this W3 belongs to R K cross H. And then this B3 belongs to RK. Now these are the weights. And now you can put some numbers. So this is not, this should look like RH. Okay. Now you can add up these things for some simple thing, and then you can see how many weights are there here. Okay, this is actually weight heavy. Now to avoid this, they came up with actually the GRUs. Okay, so now let's implement these things. So now what we will do is, now we will go ahead with a simple classification. So okay, now the unrolling, let it be any cell. Okay. The overall idea will be, you have a cell, you get HT minus 1. This is your XT. You perform some operation, and the output will be HT, and then what you get is YT. Okay, this is what you get. Okay, this you unroll multiple times. The unrolling, sometimes they refer it having a thing here. Now this is for GRUs or RNNs. In terms of LSTMs, now you don't have one. Now you actually have two things. This is CT minus 1, HT minus 1. You get this XT here. Then you get CT, HT, and you take this HT and perform some modification, and then you get YT. Okay, you don't see here the modification with only with respect to HT. Now this is one cell. Again, you can have recurrence also. And this is the idea of LSTMs. Okay. Now each time whenever you are unrolling, you will be getting this YT. If you consider only the Y capital T to perform some classification, okay, that is fine. Or at each of this YT, you perform some other, use some MLP and then perform transformation. That will be your sequence to sequence. Okay, for each of these YT, now you have some other MLP that will give you some other output. Okay. Now, for example, if you want to predict the next word, now the MLP will be, the output will be the size of the whole, how many words that are there. That is what is known as a dictionary. That will give you uh, the output in the case of sequence to sequence. Okay. Now here, now you have only one cell that is repeating multiple times. On the other hand, now what they do is, now they will have now what is known as deep deeper network, where which you can specify the number of layers as well. So I just go ahead and write with for the LSTMs. Okay. Now, why am I writing it for LSTMs is actually it is easy for us to okay. Now let's say that you have three LSTM cells, you have three layers. Okay, three layers of them. Okay. So now let's say that it is C0, this is H0, and the input is X0. Now this will give you C1, and then this is H1. Okay. Now you take this H1 which is there and give it as an input for the another one. Okay. Now see here. Here you used to give X0. This is your first input of the sequence. You take the hidden state here and give it to this. And again you will have C1. Sorry, this is C0 and H0 of the another layer. Now this will give you C1 and H1. Now again what you will do, you will take this and give it as an input. Again for these you will have C0 and H0 of another layer. This will give you C1 H1. Okay. And then what do you do if you want to go ahead with a sequence to sequence? You take this HT which is there and then you pass it through an MLP, and then finally you use softmax here to get the output. Now considering that you are predicting the next word. Now this is for one sequence. The same thing you repeat. What do you mean by repeat? These are the same weights that are there. Okay, now you have another thing. For this you will have X1. That will give you two things. You give it to the next one. Now so on and so forth, you repeat. Now when I say repeat, not only the weights of this are repeated, even the weights of MLP are repeated. Okay, you repeat them and then you go ahead with the sequence. Now if you are not doing it, you just want to perform a classification. Now repeat it for t number of times. Whatever is the last HT which is there of the highest layer, you take this, have an MLP, you pass it through the softmax in that case, and you get the predictions, the predictions in this case. That is what you use it for the classification task. Okay. Now this is how we can have multiple layers of it. Okay. Now this is how we build the architecture. Now, we haven't even come to the implementation of it. This is how we build the architectures. Okay. So this is where we actually stop this tutorials. In the next part of this RNN tutorials, we will be looking at the implementations of RNNs, GRUs, LSTMs, and their deep variations. Okay. I hope you understood the RNNs, LSTMs, and GRUs. We'll meet in the next part of this tutorial. Thank you.